everybody, and welcome to the Azure Cosmos DB Global User Group for October 2023. I'm your host, Jay Gordon, and I am a program manager with the Azure Cosmos team. And today we're diving deep into the future of search technologies, specifically focusing on vector similarity search with Azure AI Vision and Azure Cosmos DB for Postgres SQL. Now, this isn't your everyday keyword-based search. Vector search offers a richer and more sophisticated querying experience. Now, I am thrilled to introduce our guest for today. It's Platini Savidu. Please excuse me. I have terrible American Brooklyn English, and I'm going to do my best to say everybody's name correctly and say every other place correctly. So please bear with me. Platini is not just a final year electrical and computer engineering student at Aristotle University at Thessaloniki in Greece, but she's also an enthusiast of IoT, AI, cloud technologies, even biomedical engineering, and she's so passionate to technology and has earned her title of Microsoft MVP in AI. Excuse me for leaving my email up. That was my fault. Moreover, she plays an active role in the Microsoft Student Learn Ambassadors community, a really, really amazing community that we work with. She's got a great blog, and I'm just really, really glad to have her with us today. And we're going to talk a little bit about using the vector search capabilities with PG Vector. But before we do that, we've got some housekeeping that we always do when we run these sessions. And to help me with this housekeeping, I have my friend from Microsoft Reactor, Askia. Hi, Askia. How are you today?
I'm good, Jay. Good to see you again.
Good to see you again.
Yeah.
So I know we've got our code of conduct, and I want you to be able to tell everybody about it. So feel free.
Yeah, the key is just to be respectful. We want to create an environment that is respectful for both our audience and presenters. So just make sure when we, definitely want to encourage engagement in the chat, but just be mindful, respectful of others, other people's opinions, other people's differences. We'll definitely be sharing useful links throughout the chat. So definitely would like your participation. This session is going to be recorded. So for some reason, if you have to leave early, it will be available within 24 to 48 hours on the Microsoft Reactor YouTube channel, and sounds like on the Microsoft developer channel as well. This session will take about an hour. And we'll have time for questions throughout. So make sure you put those in the chat. Once again, just be respectful. And we'll turn it back over to you, Jay.
Thanks much. I will see you at the end of the show. Always appreciate you helping me out. So to help me out today, I have my guest, and it is Fatini. And here we are. Thank you so much. And please, I beg of you, forgive me for any mispronunciations. I'm trying my best here.
Hi, Jay. And hi, everyone.
So we have a spectacular conversation we're going to be having today. I'm going to give you all the space in the world to talk to our audience all about using PG Vector, specifically using vector search within Postgres, and talking about how you're going to use AI Vision. But before we get to that, and I always love this part of doing these sessions, is I like kind of keying in on the things that you do, that you work with, that basically got you here today. So why don't you tell us a little bit about yourself, what you've been doing, what you're going to be doing, and what you're working on?
Yeah, sure. So now I'm a student, I'm a final year, and I hope that I graduate next month. And my journey started almost 3.5 years ago, and when I joined the Microsoft student community, and I immediately started learning all the things about Azure technologies. And I became more and more involved in the student community. I started speaking at events, sharing guides in my blog, and I found out that I really liked the world of cloud technologies, and I want just to work more in this field.
Well, speaking of cloud technologies, I think that's one of the things you're going to be presenting to us today. And I'm really looking forward to seeing your presentation. And I know you've got a demo waiting for us. Uh, but that being said, this is an interactive user group. We want your questions. So you'll see we have our comment section. Please leave your questions there. We would love to hear them. So just put them in the chat and we will address them as soon as we can. So we've got about 50 minutes or so. So I'd love you to go ahead and just start rolling into it. I've got your presentation up. Why don't you go for it? All right.
Yes, perfect. So as they said, we're going to talk about vector similarity search using Azure AI Vision and Azure Cosmos DB for Postgres. I have already talked about me, and they did a very warm introduction for me. If you want to get in touch with me, you can use the links that are shown in this slide. And you can find my website at sfotini.github.io. So before delving into what vector embeddings and vector similarity search is, I want to understand the problem that we're trying to solve. First, I have a couple of questions for you. Uh, Firstly, have you ever looked for something like a movie, but could not remember its name, or you can't find the right keywords to search for it? Or maybe you are trying to find a product, and you have a basic idea of what a product looks like. For example, how a pair of shoes looks like, or you have the actual image, but you don't know how to search for it. And unlike traditional search systems, which rely on mentions of keywords, tags, or other metadata, lexical similarity, and the number of word occurrences, vector search systems leverages machine learning to capture the meaning of the data, allowing you to search by what you mean. And vector search work with different types of unstructured data, including text, images, videos, and audio. And for example, if we return to the second question, using a vector search system, if you want to find a product that looks like a product that in a vector search system, if you want to find a product that is similar to a product that you have, you can use the actual image of the product to search for similar products instead of trying to find the right keywords to search for your product. And this is much easier than traditional vector search. And vector search relies on the conversion of images and text and audio and videos and other type of data into an numeric representation, which is called vector embedding, and uses algorithms like nearest neighbors to find objects that are similar to your desired object. And this is what we are going to explore today. We will start by exploring the concept of vector embeddings and understand how we can generate vector embeddings using machine learning models. And then we will understand how a vector search system works. And we will build the basic vector search system using the Azure AI Vision embeddings model and the Azure Cosmos DB for Postgres for storing our data. Okay, I think we can start with the main presentation. And so, what are vector embeddings? As I said, vector search is based on the conversion of unstructured data into a numerical representation, which is called a vector embedding. And you can think of vector embeddings as an array of numerical values. This array is high-dimensional and dense, and each dimension of a vector contains information about the original content. So by converting data into vectors, we can capture the meaning of the data and the semantic similarity between two objects. For example, the words cat and kitten are semantically similar, and so we expect that the vectors will be numerically close. Or alternatively, if we place these vectors in the same vector space, we will see that the vectors of cat and kitten will be close to one another, while the vector of puppy will be far apart of these vectors. And so we can quantify the semantic similarity by their proximity in the vector space. And to measure the semantic similarity, we can use a distance metric, such as Euclidean distance, inner product, or cosine similarity. Today, I'm going to use cosine similarity and cosine distance. And cosine similarity is defined as the angle between two vectors, which is equal to the dot product of the vectors, which is equal to the dot product of the vectors divided by the product of their magnitudes. And cosine distance is equal to 1 minus cosine similarity. And the reason why I use this metric is because Azure AI Vision uses this metric to compute cosine similarity. Now, in the vector search system, the vector appending of the user's query is compared with a set of pre-stored appendings to find the vectors that are most similar to the query vector. So in this example, we first compute the vector appending of the word dog, and we place this vector in the same vector space. And then we rank the remaining object by similarity to the query vector. And it's very important to, in order to compare the vectors with the query vector, we must use the same embedding model to generate all these vectors. And with that being said, let's try to understand how we can generate vector embeddings for our data. Is it as simple as converting our data into numerical representation? And the answer is no, because we want to ensure that the original meaning of the data is preserved. For example, if we want to compare two sentences, we don't want to check whether the two sentences contain all the same words, but we want to check if the meaning of the two sentences is the same. So we need an embedding model that is capable of converting unstructured text into a numerical representation which captures the original meaning of the data. Most embedding models are based on machine learning models and specifically neural networks. For example, OpenAI, which is very popular in the last months, offers some embeddings model which are capable of generating vector embeddings for pieces of text. Today, I will use the embeddings model of Azure AI Vision for vectorizing images and text. So Azure AI Vision is powered by Project Florence, which is a state-of-the-art computer vision model developed by Microsoft Research. Florence is a large foundation model which is based on transformers and is capable of handling both language and vision-based tasks. It can train on 1 billion of text image pairs and videos and can be adapted to a variety of computer vision tasks such as classification, object detection, frame locator in videos, image captioning and image retrieval, which is the functionality of Azure AI Vision that we're going to explore today. Before going into details about image retrieval, let's go to the Vision Studio, which is a UI interface for Azure AI Vision, to explore the Azure AI, the image retrieval functionality. With the image retrieval, you can search over a collection of images using natural language text prompts. To run image retrieval in Vision Studio, you need a cognitive service resource in the US region. But if you want to use the SDKs, you can create a cognitive service resource in any of the available regions. We start by selecting a photo collection, and then we can send some text prompts to search for images. For example, I can search for images showing sunset in the mountains. And here we can see the results, which are pretty accurate. We see sunset and mountains. We can also search for sunset on the beach. And again, we see that the model retains the correct results. And you can also search using your own search query. For example, I have seen that the image collection includes some photographs of elephants, so I will search for an elephant. And as you see, the AI Vision retains images of elephants, and there are some images that does not contain elephants, but this is okay because the photo collection is limited and doesn't include so many photographs of elephants. So let's go back to the presentation and see, let's try to understand how the image retrieval flow in Azure AI Vision works. First, we use the vectorized image API to convert the images in our collection into vector embeddings. And when a query is issued by an application, we use the same embedding model to compute the vector of our query. And if the query is a text prompt, we can use the vectorized text API. Or if it is an image, we can use the vectorized image API. Then we use the query vector and the vectors of the images in our collection, and we compute the cosine similarity between any two vectors. And then we can sort the results and select the vectors with the highest cosine similarity, and we can access the images that are associated with these vectors. Okay, let's jump into the second demo, which is a Jupyter notebook, in which we will try to build this flow using Python. I will use some images from the paintings dataset of Visual Geometry Group at the University of Oxford. First, you have to import the necessary libraries and some functions that I have created to make post requests to the vectorized image API and to the vectorized text API of Azure AI Vision. Okay, it's slow for some reason, but so we can see the result. Okay, then we log the environment variables for Azure AI Vision resource. And now we can start exploring our dataset. I will open the first image, which is a painting of a dog. And we use the image embedding function to send a post request to the vectorized image API and compute the vector embedding of this image. Next, let's try to form some text prompts and compute the cosine similarity between the vector of the image and the vector of our query. As you see, this is an image of a dog. As a first text prompt, I use the text prompt and dog. And as you expect, the cosine similarity is very high, is 36%, which is very good. But we can find a better cosine similarity score. Then the type of this painting is a terrier dog. So we can run the next code block, and we'll see that the cosine similarity is almost 41%. And if we be more specific and use a text prompt like a painting of a terrier dog, we will see that the cosine similarity is 1% higher than the previous cosine similarity. And as a last step, I will use a text prompt of a totally different thing. For example, a car. This is definitely not a painting of a car. And we will see that the cosine similarity is much lower. It's almost 19.5%. So this painting does not show a car. We can also compare two images. So I will open two more images from our dataset. The first is an image of Hannah the dog, and the second is a painting of apples on a table. And now we will compute the cosine similarity of the vectors between any two images. And here I want everyone to take a moment and think about what do you expect? Which cosine similarity score will be high? Will the cosine similarity between image 1 and image 3 be higher than the cosine similarity score between image 1 and image 2? As we said, cosine similarity is a metric of the semantic similarity between two objects. And we see that image 1 and image 2 are paintings of dogs, so we expect that the cosine similarity score will be higher than the cosine similarity score between any other pair. And we can also compute the cosine similarity scores, and we see that the cosine similarity between the paintings of dogs is 75%, while the other two cosine similarity scores are almost 40%, which is a much lower value. Now, in the next part of the notebook, we'll generate vector embeddings for a collection of 85 images from our dataset. And we will then send some text queries and use images as a reference image to search for similar paintings in our okay, I think it's not a good idea to run the notebook live, so I will not run the next save. Okay, let's move on, and I will come back to show you just a display of some of the paintings that are included in the dataset. Okay, it ran. So here we see that the dataset contains paintings of animals, of fruits, of vegetables, landscapes, and some portrait of people. Now we can generate embeddings for all the images in the dataset, and we store these embeddings in a JSON file. And now we can load these embeddings to use them in the next examples. I want to mention that you can find all the scripts and the notebooks that I'm showing today in my GitHub repository. And if you don't see the link in the description of the video, you will see at the end of the presentation, so you will have the time to explore the concept on your own. So the first scenario is image-to-image scenario or reverse image search. We will use an image as a reference to search for similar paintings. Here, the search by image function first computes the vector embedding of our reference image, and then computes the cosine similarity between the reference vector and the vectors of the images in our collection, sorts the results, and selects the 8 vectors and the 8 images with the highest similarity score. We see that this is an image of a brown horse, and the paintings that are returned by the function show brown horses and a white horse and another white animal, but generally the results are pretty accurate. In the next example, we will use this image as a reference, which is a boat. And now we see that the results that are returned by the function are not semantically similar as in the first case, but we can still see some similarities in the colors of the paintings and in the basic shapes that we see in these paintings. You can also search using another image, for example, a painting of flowers, and you can get pretty accurate results. We see paintings of flowers. And in the last example, I used this image as a reference, which is a pink table with vases, flowers, and some books on it. And we get, as a result, paintings that depict tables with flowers and vases and books and chairs. So the results are good. And also, this painting is from the same artist as the reference painting. Now let's see a text-to-image search scenario, which is the scenario that we saw in the Vision Studio. Now we search based on text query. For example, let's try to find paintings of a table with flowers. And the search by text function works in the same way as the search by image function. The only difference is that in order to convert our search term into a vector, we use the vectorized text API instead of the vectorized image API. And we see again that the function returns paintings of a table with flowers, so the results are accurate. And you can also search for paintings showing apples, and you can get paintings of apples with different colors and shapes. And you will see here that it's a painting of apples and mushrooms, and the similarity score is 30.6%. And if you try, you can try to improve the similarity score by improving the search term. For example, if I use as a search term mushrooms and apples, you will see that the similarity score is 43.5% and is almost 13% higher than in the previous example. My dataset also includes some paintings, 6 in total on Vincent van Gogh, and you can use the name of the artist, for example, Vincent van Gogh, to try to search for paintings of this artist. In my case, Vincent van Gogh is famous, so I am able to find all the paintings of this artist. And there are some paintings that are not from Vincent van Gogh, but they have lower similarity scores. This is a portrait on Vincent van Gogh, so if you change a bit the search term, you can find the portrait with high cosine similarity, and you can also get some other portraits from different artists, and the similarity scores are better than in the first case. Okay, I have some other examples. For example, this is the type of a painting in my dataset, and using this function, I'm able to find this painting with high cosine similarity score. And you can also detect activities in the images. For example, find paintings that show people playing chess, and you will see that you are able to find paintings of people playing chess. That's it. So back here, back in our presentation, we are going to talk a bit about vector databases. In the demo that I showed you, the vector embeddings are stored in a pandas data frame, but this is not an effective way to store a large amount of data. And this is why we use vector databases. And vector database is a specialized type of database which is optimized for storing and querying vectors with large number of dimensions. So in our example, we can store the vectors of our images in a vector database and then send queries to this database in order to retrieve the results. Azure offers different types of vector databases, and most of the vector databases are built on the top of traditional databases with specialized extensions. And today we're going to explore the vector similarity search capabilities of Azure Cosmos DB for Postgres. And let's start it. In Azure Cosmos DB for Postgres and generally in Postgres SQL databases, vector similarity search is enabled by the PG vector extension. And before storing any vectors in your database, you should install the PG vector extension using the select create extension vector command. And then when creating a table, you can use the type vector to create a column in the table to store vector embeddings. So this command create a table named image vectors with two columns. The file name column of type text includes the name of the image file, while the embedding column of type vector contains the vector embedding of the image file, which is generated by Azure AI Vision. And I want to mention that next to the type vector and in parentheses, you can specify the number of dimensions of your vector embeddings, which is different depending on the embedding model that you will use to generate your vectors. This is the table that I will use in the next example, where in this demo, I'm going to show you how to use Azure Cosmos DB for Postgres for storing your vector data, Azure AI Vision for generating the embeddings, and Azure Blob Storage for storing the images in your dataset. I will use the same dataset, the paintings dataset by the Visual Geometry Group at University of Oxford, which contains more than 8,000 images of paintings. And I have already uploaded the images in the Azure Blob Storage. And for each image that's stored in Azure Blob Storage, I call the vectorized image API of Azure AI Vision to compute the vector embedding of this image. And then I save in my table in Azure Cosmos DB the file name of the image and its vector embedding in the table that I have created. I have already executed this flow because it takes some time to complete. But as I said, you can find all the scripts in my GitHub repository if you want to explore this process on your own. And now we'll jump into the next flow, which is the vector similarity search flow. Again, we'll use Jupyter notebooks as our application, and we will call the vectorized image or text API to compute the vector embedding of our query. And then we'll use the query vector to form SQL queries to our Azure Cosmos DB for Postgres table to retrieve the most similar images. Let's go back to Visual Studio. And this is the second notebook. Again, we'll first import the libraries that are necessary to run this app. And we load the environment variables for Azure Cosmos DB, Azure AI Vision, and Azure Blob Storage. And then I need to connect to my Azure Cosmos DB for Postgres cluster. To do this, I first create a connection pool. And then I create a cursor object, which is used to execute SQL queries. Here you can see a demonstration of the first 10 rows of our table. You can see the file name of the image, and next is the embedding. Of course, it's not displayed here because it's too big. And now we will explore the two scenarios, the image-to-image scenario or reverse image search scenario, and the text-to-image scenario. Before going into image retrieval, we have to define a helper function which will be used to display the images that are retrieved for Azure Cosmos DB. And the display image read function takes as a parameter a list of the file names of the images, downloads these images from our Azure Blob Storage container, and then displays these images in a plot. So let's start with the text to image search scenario. Again, I will use the same query as in the previous demo. And let's say that we want to find paintings that show a table with flowers. We first compute the vector embedding of our text prompt using the text embedding function and the vectorized text API. And then we use this vector to form a SQL select statement to our table. And let's try to understand how this select statement works. This query computes the cosine distance. This is the operator for cosine distance between the query vector and its vector embedding that's stored in our table. Order the results based on the computing cosine distance, and then selects the 12 vectors with the highest cosine similarity score. And here you can see the results that are retrieved from for Azure Cosmos DB. Using this select SQL query, we can find the file name and the corresponding vector embedding of the paintings that are most similar to our text prompt. And using the display image function, we can display the paintings that are retrieved from Azure Cosmos DB and Azure Blob Storage. As you may notice, using this select statement, we are not able to find the cosine similarity score of the retrieved images. But if we modify a bit this select statement, we are able to retrieve the cosine similarity score. So this select statement selects the file name and the cosine similarity, which is equal to 1 minus the cosine distance between the query vector and the vector embedding of the image. And now in the results, we can see that we can find both the file name of the image and the computed cosine similarity score. And again, we can use the display multiplicate function to display the results along with the similarity score, which is retrieved from Azure Cosmos DB. In this example, we want to filter the results based on the cosine similarity value. To do this, we use a where clause, and we select only the images and the vectors that have a cosine similarity score which is higher than a predefined threshold. And you can see that the results that I'm trained for Cosmos DB are only 6 and are only 7 and not 12 as in the previous case. Now we have the image-to-image search scenario. And in the first example, I will use as a reference image an image that's not contained in our dataset. This is a painting of apples, and I have computed the vector embedding of this image using the vectorized image API of Azure AI Vision. And I use a similar select statement to find the paintings that are most similar to our reference painting. The difference is that here I use the vector embedding of our image. And you will see that the Azure Cosmos DB for PostgreSQL returns the paintings along with the similarity score.
Do you think we have a second for a question?
Yes.
We got a few in, and so one of them is I wonder about performance comparison of PG Vector versus a native vector database like Weavate, Chroma, LanceDB.
Okay, I have not used any of these databases, so I cannot actually answer this question. But I have to say that the performance of Pidgin Vector can be improved if you use indexes and approximate nearest neighbor algorithms instead of the exact nearest neighbor algorithm that I'm using in this demo.
Okay, and then we got one more question. I wonder how the cosine similarity of image to image compares with the cosine similarity of text descriptions generated by the model.
Okay, I'm not sure that I understand this question, but I think that you're wondering why the cosine similarity between two images is higher than the cosine similarity between an image as a text.
Well, sorry, go ahead.
Yeah.
Well, I was going to say that Sean can always reach out to you after the fact. I know you've got your information on LinkedIn and all that. So he can, if he wants to expand on his question, I'm sure that he can do that there. You've got about 12 minutes left today. So I just want to make sure you're all be able to finish up. The one thing that we'd love to see if you can provide is the a repository link to the actual notebook if you don't mind. We'd love to see that. I know our viewers would like that. We can get that via the notes after the fact. So I'll just grab that for you. We'll put in the notes. Anyway, like I said, we got about 12 minutes left. I'm going to give it back to you. All right.
Perfect, thank you. I just want to add something for the last question. And the cosine similarity between two images is always higher than the cosine similarity between a text and an image, because two images have always more dimensions in common. For example, when comparing two images, we do not only compare if both images contain arrows or contains a tail, but we compare the colors between any two images, the shapes that we see in these images. But when using text, we cannot describe all these aspects of the image, so we get a lower similarity score. But this doesn't mean that the cosine similarity of the text from it's not good. You just need to use different thresholds when doing image to image search and when doing text to image search. Okay, and before the end of the presentation, I have my last example. In this case, instead of using an external image as a reference for searching for similar paintings, I will use an image that is included in my dataset, and I have selected this painting, which is displayed here. And now when I write the select statement, I don't have to directly specify the vector embedding of this painting, but instead I can use this statement to retrieve the vector embedding of this painting from our table. Use this vector embedding to compute the cosine distance between the reference vector and the vector embeddings of all the other images in my dataset. And here we can see the results. Yeah, you can also modify a bit the previous select statement to retrieve the cosine similarity along with the file name and the vector embeddings. So this was a quick introduction to the PG vector functionality. As I said, you can start exploring more advanced features such as indexing and using approximate nearest neighbors algorithms, and ways you can optimize the performance of PG vector in Azure Cosmos DB for Postgres. And you can find more information about this topic in the GitHub repository of BC Vector. I'm going back to the presentation to show you some useful resources to learn more about Azure AI Vision image retrieval functionality, and how you can use the vector similarity search feature in Azure Cosmos DB for Postgres. Here's an article that I have written about building a simple vector similarity search app with Azure AI Vision and Azure Cosmos DB for Postgres. And the last link is the GitHub repository that contains all the notebooks and scripts that I showed in today's session.
Great. And what we'll do is I will get all those links from you before we finish up, and I'll put those in the show notes, so people, if they need any of these resources, they can go and grab them. So I guess, do we have any questions from the audience? I'd love to give everybody a chance. If not, we can start wrapping up. Either way, I think that you put together a really great presentation today. I learned a lot. I know our viewers learned a lot. And Askia, did you learn a lot today?
I did. I absolutely did. Yeah. It's every time it's a pretty interesting and knowledgeful experience. So I definitely appreciate the time and the presentation. It's good.
Yeah,
Great job.
so great. So I want to, before we completely close out today, Askia, do you have any information about a survey or anything people can
Yeah,
take?
I sure do. Yeah, if you want to bring up my slide, I will. We've got our survey link there. So we'd love to hear your feedback, what you thought of the presentation today. So go ahead and use that link, and then make sure to enter the event code, which is 20517, and that will reference this session. And we will definitely take any comments into consideration for future live streams.
Spectacular. Well, everybody, I'm going to leave this up for you for just a second. Fatini, are there any presentations, anything that you've got coming up that you'd like to share with our audience before we kind of close out?
I have not planned anything for the next month.
Okay, fair enough. I'm not planning anything for the next month myself, but that's a personal issue. I just want everyone to remember that next month, November, is Microsoft Ignite. If you have not registered, go to aka.ms/msignite. You can go ahead, you can register for that. I'm going to be there out in Seattle. I'm looking forward to seeing a bunch of you. If you would like to have a conversation, I know that there's going to be some great people who are going to be meeting with you. They're going to be experts. I'll be at one of the expert booths, so we'll be able to talk. But anyway, Fatina, thank you so much for today. You did such a wonderful job, and I'd love to have you back on at some point. I want to see you continue to progress. I know that after you graduate, you've got so much more to do. And so thank you very much for being part of this today.
Thank you very much. I have a very great time here.
Great. Well, unless anybody else has anything else, stop that, Alexa. Alexa decided to chiming in. There's AI for us. Anyhow, unless anybody has anything else to chime in with, I think we're going to roll out. Thank you very much for watching today. And I know that we've got a lot more great stuff to come. We've got sessions set up for November and December. We'll see you then. But until then, let's give everybody a big wave goodbye. So long, everyone. We will see you next time. Have a great one. Thank you. Bye now.
Thank you.
Bye.